We have usually we know that magnetic materials. Okay, these magnetic materials depends on its magnetic moment or orbital angular momentum of an electron inside the atom is divided or classified into three types. That is, one is diamagnetic material, another one is paramagnetic material. The most important one is called as ferromagnetic material. Okay. Now you can see here how the behavior of diamagnetic material takes place, how the behavior of paramagnetic material takes place, and how the behavior of ferromagnetic material. Okay, first of all, let us see here. By comparison, we are discussing, therefore, it will be understood very clearly. Diamagnetic material. The magnetic material are the substances which are feebly repelled, means weakly repelled by a magnet, means which never attract, it repels. Such type of substances we call it as diamagnetic materials. For example, antimony, bismuth, copper, gold, silver, quartz, mercury, alcohol, water, hydrogen, air, organ. These are all under categorized as diamagnetic material. Same way, if you see paramagnetic materials, these are the materials which are the or materials or the substance which are feebly attract, means it will attract towards the magnetic material or towards the magnetic substances or magnet, simply I can say. These are the substances which attracts towards the magnet is called as paramagnetic material. Attracts in the sense very less amount of attraction takes place, not like exactly magnetic material. Now coming to the ferromagnetic material, these are the substances which are attracted by the magnet very strongly. These are the materials we call exactly the magnetic materials. That is, like we know iron, cobalt, nickel, gadolinium, and dysprosium. These are alloys. Gadolinium is a direct material. Dysprosium, etc. Some of the other alloys behaves as a ferromagnetic substances. Now, let us say how the behavior of the diamagnetic materials. When you place in any magnetic field the diamagnetic material, the magnetic lines of force or the lines of force which is tend to avoid the substance, means since it is feebly repelled, it will not allow to itself. See here, I substituted in the magnetic field in that. So the magnetic field lines are the force of lines which are not allowing through itself. But coming to the paramagnetic material, the lines of force prefer to pass through the substance. They are preferring, but very less number of force of lines. Coming to the ferromagnetic substances, more number of lines can pass through the material. So, this is the way the behavior of ferro, para, and diamagnetic substances we can understand. Next, when we place in a non-uniform magnetic field, it moves how? Obviously, when if you place a non-magnetic material or diamagnetic material in a non-uniform magnetic field, then it moves stronger to weaker direction. It is repelling. So stronger direction to weaker direction, it rotates. Whereas when it is placed, paramagnetic material, when you place that from weaker to stronger direction, it try to move. Weaker to stronger direction, it try to align. Obviously, ferromagnetic material itself is magnetic material, so this is always weaker to stronger, very faster it will move. Next, coming to a diamagnetic rod is freely suspended in uniform magnetic field. How it behaves? It aligns itself in a direction perpendicular to the field. It aligns itself perpendicular to the field direction. But coming to the paramagnetic rod, if you suspend in uniform magnetic field, it aligns in the direction of magnetic field or parallel to the magnetic field. Whereas If you place diamagnetic substance in the uniform magnetic field, sorry, ferromagnetic substance in uniform magnetic field, automatically it aligns itself in the direction of magnetic field. This is very faster here. Look at here, perpendicular in the diamagnetic substances. It moves parallelly, and when coming to ferromagnetic material, very fast. Means the difference is that it's slowly, feebly it is attracting, as fast it is attracting, it is repelling. Now, let us say some liquids, diamagnetic liquid, water, or in a watch glass if you are taking. Why watch glass? It is transparent, it is visible. When you keep between the poles very closer to each other, you can find how the shape has come. Means from this side and this side it is repelling this liquid. Okay, since it is repelled by these poles, then here it is like bulging area you are finding. Here it is wet surface you are finding. But whereas here it's weakly or feebly attracting. Okay, so it is gets pushed so like this. The same liquid if you keep or if you give here, it is opposite to in this case. Now, in this, little more the effect comes here than this. So, this is happening in the case of different paramagnetic liquid like this and ferromagnetic liquid is like this. Now, when diamagnetic substance is placed in a magnetic field, it is weakly magnetized. Obviously, when you substitute any material in a magnetic field, it will not, it repelling its field. So if you are applying more field, it is weakly magnetizes. But coming to the paramagnetic materials, if you are substituted or placed in a high intensified magnetic field, it is magnetized but not like a ferromagnetic materials. Now, when ferromagnetic substance is placed in a magnetic field, it is strongly magnetized in the strong direction, in the direction of the magnetic field. Now you can see most important characteristics which we have learned in earlier classes, that is induced dipole moment is a small or negative value. Here induced dipole moment is positive in paramagnetic field. Obviously in diamagnetic material the dipole moment is more positive because it is aligns in the direction of magnetic field, but it is opposite. Intensity of magnetization. We studied what is intensity of magnetization. Intensity of magnetization is nothing but the substance which you substituted or which you place in a magnetic field adapts the magnetic field or magnetic properties. How far, to what extent it is adapting the magnetic properties, that is we call as intensity of magnetization. That is negative for diamagnetic material because diamagnetic material will not adapt. In spite of that, it repels. That's what negative. Intensity of magnetization for paramagnetic material is positive but less amount of intensity of magnetization. For ferromagnetic material, it is very large and positive. With respect to this, you can understand most important characteristics. Magnetic permeability is lesser, always less than 1 for the diamagnetic material and positive or equal to 1 for the paramagnetic material, greater or larger for the ferromagnetic material. Same way, chi value. Chi in the sense magnetic susceptibility. Magnetic susceptibility has a small negative value for the dia and positive for the para, highly positive for the ferromagnetic material. Now here we need to discuss one more important thing which is called as Curie's law or Curie's temperature. What is this, sir? Curie's temperature. Curie is a scientist name. With respect to him, up to certain temperature, the magnetic material behaves magnetic properties with respect to the temperature as a magnet. But once we cross the Curie's law, optimum temperature, then it turns into, or it will lose its magnetic properties. Then ferromagnetic material turns into the para. Para will turn into the dia. Okay. So the temperature where ferromagnetic material is turns into paramagnetic material, that is called Curie's temperature or Curie point we call. Okay. So that is with respect to magnetic susceptibility as explained here. Magnetic susceptibility of a material varies inversely with the absolute temperature. That is we call as Curie's law. That is I is directly proportional to h by t, where h is a magnetization of magnetizing field by T is a temperature. So we know that I by H is gives us the susceptibility. When you write I by H, that is directly proportional to reciprocal of temperature. So when I remove the proportionality, I'll get constant that is called as Curie constant. Curie constant. So Curie temperature is different for the different materials. For iron is it 1000 kilometers, sorry, extreme 1000 kelvins, and for cobalt it is 1400 kelvins, and for nickel it is 600 kelvins. If this temperature crosses for iron, it turns as a paramagnetic material. The graph you can see the variation with respect to intensity as well as susceptibility.
Sir,
Yes, tell me.
so what is the absolute temperature?
Okay. Here, absolute temperature is with respect to the 0 Kelvin temperature. It is. Uh,
Okay.
Actually, the definition of the 0 Kelvin temperature, normally we think that according to thermometer, 0 degree centigrade is a zero value. But Kelvin, when he was a scientist, 0 degree centigrade is a temperature he did not satisfy with that, because that time temperature is not behaving as a zero. Therefore, what happened, the Kelvin again, he started researching on that. He was a professor while he is explaining that. Since he did not satisfy with the definition, again he went back as a student in the same university. He's worked out, he found the definition for the temperature. The definition of the temperature is that whenever, if you take any substance, in the substance, vibration of average kinetic energy of a vibration of a molecules is equal to zero. That means if you take ice cube, which is at the negative temperature also, there are some vibrations better. Okay. So whenever this vibration cease in the sense completely should stop it, then we can say it is as a Kelvin temperature or absolute zero temperature of that particular material. So Kelvin has researched, he found absolute zero temperature is nothing but when the vibration of the particles will stops, that is the absolute temperature of that particular substance. He has given the definition. Okay, that is we call as zero Kelvin also. Got it?
Yes, sir.
So that's why with respect to Kelvin temperature, in terms of Kelvin, we will count. That's why Kelvin we are using whenever higher temperatures we are considering, that time we will use the Kelvin. Now, before this, whatever classification of materials which we have seen, diapara, ferro, that is used in another subject also. But now, whatever we are going to discuss, this is most important. Hysteresis loop or magnetization curve. First itself, I am giving the hint or trial for this topic. Hysteresis loop means what? Hysteresis word itself is telling that history of the material or history of the magnetic materials which we have used in this. or which you are magnetizing the magnetic material. Means whatever you are going to discuss, it is not depending on the whatever you are applying. It depends on its history of the material. For example, I'll tell you simple. Somebody so and so X person is there. That X person is estimated usually by his history. Okay, he is belonging to so and so like that. Means with respect to the history, they are estimating the performance of that person there. Same way here, when you are taking any substance, the substance behaves. For example, iron. Iron means it behaves like this only. Steel, it behaves like this only. It is depends on the its history. Okay, cobalt like this only. Of course, there are some characteristics with respect to this curve we will understand. That is called as magnetization curve. This hysteresis loop, how we are going to obtain. Remember here, we are going to obtain the hysteresis loop with magnetization or magnetizing field, that is H, as well as intensity of magnetization I. Between them, how the magnetic field is adapted by the a substance we are going to understand. That previously we were discussed definitions, these two, right? With respect to the definition, now what I am going to do in the sense, I have chosen like iron or a steel material. I am placing in the magnetic field which is supplied by the H. H is nothing but magnetizing field. We say it is nothing but source of magnetic field. And along the y-axis, I am taking the adopting the magnetic properties from the source. Who is adopting the substance, magnetic material which I kept in the magnetic field, right? Between these two, I'm going to obtain the curve or loop which is called as hysteresis loop. Look at here. Now, what you understood from here, from O to certain extent, it has reached one curve. Then here in this case, I have substituted in the sense there is a material I placed in the field, field of whom H. Then whenever I placed, this intensity has increased. Okay, means it is adapting the properties of magnetic field, right? Slowly it is magnetizing. What it is becoming? Magnetizing. Okay, it has magnetized. So from O to this position has reached. This is the saturation position. Further, further, if you supply also, or if you are supplying source field also, it will not take. Why? See, I'm a person. I'm eating a food. I will eat what I need, what I want, up to what extent I can eat. I cannot eat more since I have the more food here, right? I can eat the food whatever I can eat, whatever it is fit for me. I cannot eat since it is more food it is available, so I can eat more. No, it is not like that, right? It is reached the saturation position. Now, after that, what did I do here? I am demagnetizing it. Once it is magnetized, what I am doing here? Demagnetizing, demagnetizing it, right? Demagnetizing in the sense slowly by applying opposite magnetic field or the magnetic field which is whatever I am supplying in opposite way if I apply, then there is a demagnetization starts. That is from the saturation position to this position it has come. This is the position you are seeing here, the mark whichever I kept here. That mark here with respect to y-axis, it is not at the zero, but with respect to x-axis, this is at the zero. right now. So again, from here to here it has decreased. Now with respect to y-axis it is 0, right? So this is a property of coercivity, we call coercivity. Okay, and this is a property also we explains retentivity, means it is not completely zero, but you can see. Now I have I have applied the magnetic field in opposite direction, therefore it is completely zero. Again, it is demagnetized. It went into the negative region. Now, what I am doing? Again, I am increasing the magnetic field. Then it has increased via D, E, F, A. It has reached. So, therefore, what I got here, some loop I have got. This is the loop we call as hysteresis loop. This loop, why it has come that shape only, sir? Why that only? Why that's the way it has come? Because because from the origin to either sides we call it as coercivity property. O to B we call it as retentivity property. What is the coercivity? What is the retentivity? You'll understand. Intensity of magnetization I increases with the increase in the magnetizing force. Just now, as I said, it has increased OA and reaches situation at A. When H is decreased, when H is decreased, then what happen? I decreases, but it is not zero. At H equal to zero means along x equal to zero with respect to x-axis, but I is not become zero. That is at the position B, OB. That we call as retentivity. What do you mean by retentivity, sir? This is the most important topic. Retentivity in the sense residual magnetism we call. Residual magnetism. This residual magnetism is nothing but regaining of magnetic properties or retaining of magnetic properties in the particular material. What is this? Retaining of the magnetic material in the particular material is called as retentivity. Now, next one. To bring from B to C, while you are bringing, what happened? It is demagnetizing completely up to C. Okay. So for that purpose also you have applied the force in opposite direction, right? For that purpose also you have applied the force, magnetizing force in opposite direction. Therefore B to C it has come. Then whatever B to C it has decreased. Sometimes for some different materials the loop is very narrow like this it comes. But this loop it is little wider. It has come little wider. So this type of property, this magnetizing force represents coercivity. What it is? Coercivity we call it is. Okay. This coercivity indicates that how much a magnetic substance or a magnet can demagnetize. From O to how much it can move, how much wider loop it can get. That is shows the coercivity. Okay. That is O to C we can say. Now, here most important properties you have seen retentivity and coercivity. After reaching the level D, if you are continuously applying, it reaches the position D, completely it is demagnetized. There is no further, you cannot do demagnetization in that. But again, if you started reverse direction the magnetic field application, then if you are applying the magnetizing force in positive way, then it starts increasing from D. and it is not passing through the sea again. Remember, it is not magnetizing through the sea. It is going through the E, again F, again A. It is reaching. So therefore, it is completely giving a loop for us. When you are studying the characteristics of any magnetic material, while it is magnetizing as well as demagnetizing, then if you note a points each and every stage, then we will obtain a graphical mode or in the form of graph, like in a form of one loop, we will obtain. This loop we call as hysteresis loop. Here A, B, C, D, E, F, A is called as hysteresis loop. The area of the loop gives the loss of energy, whatever area, this total area is there, no? This total area of the loop gives the loss of energy due to cycle of magnetization and demagnetization. Cycle of magnetization and demagnetization, and dissipated energy in the form of heat. Obviously, when you are magnetizing, demagnetizing, there is some amount of heat energy also produces, that is called as dissipated energy in a form of heat. Excuse me. Now, you can see here a material like iron, if you keep inside the uh, magnetizing field, then we can magnetize it and we can demagnetize it. Okay, but coming to iron and steel, iron adopts the magnetic properties very faster, whereas steel will not adapt the magnetic properties very faster. It takes much time. Okay, that's why iron magnetize, demagnetize very faster, but whereas steel will not magnetize faster and will not demagnetize faster. That's why in permanent magnets, in laboratory we have normal magnets are there, no? That is made up of steel materials only, not iron. Okay, so you can see here the variation in the loop diagram as an imagination. This is a hysteresis loop, how it takes place. See, for the different material, it is different. This wider part, the coercivity, the demagnetization and retentivity, two important characteristics. Apart from that, susceptibility is another characteristic which describes the uh, T, which is used for the permanent magnet, which is used for the electromagnet. This is all about the hysteresis loop or magnetization curve. In the next slide, we will see a little more clarity for the two different materials. See, you are finding here a material which is called as hysteresis curve. What is this hysteresis curve? For steel and soft iron core. Now you are finding here soft iron core which is having very thin, the red color one. But the steel, you're finding very wider at the center point, means coercivity is more. What is the coercivity? The demagnetization for the material of demagnetization takes more time. For the soft iron, the coercivity is less, whereas the steel material, the coercivity is more. Okay, so it takes more time to demagnetize also, right? But retentivity is less in a case of steel. In the steel, the magnetic properties and residual magnetism existence is more for iron. That's why the vertical line is more than the steel. Okay, you can understand by comparison of these two. Now you can see exactly what we were discussed, how the material had changed the imagination. See, a magnetic material aligns in a form of magnetic field direction. It is reached the saturation position. The moment it has reached the saturation position, you can look at here. This is a substance is magnetized completely. What happens to that? Completely, it is magnetized. Magnetized. Okay, but After magnetizing, what we are doing, we are applying this magnetic field in opposite direction. Therefore, it is reached. After saturation position, it is returned and it has comes here. This is the why here it's supposed to come here, but along y-axis it is not zero, but along x-axis it is zero. Means applying field is zero, though you are not applying demagnetization force, okay, but in the magnetic substances some magnetic properties remainly is existing, is is existing still. That is called remanence here. The amount of magnetization it retains at zero driving field is called as remanence. This remanence is called as retentivity. What is that? Retentivity. Then from here to here again, if you are demagnetizing, then this origin to this where the loop line has come, this wider part is indicates the coercivity. It is a measure of the reversing the field with respect to the driving field. Okay, with respect to the driving magnetization. Okay, after the saturation, this will be continuous in negative direction until reaches all the domains will be diverted as a non-magnetic material completely. Then later on, if you start applying the again magnetic field as a driving field, then it returns back as in a form of loop. Is it clear? Coercivity and this.
Yes, sir.
Now this is all about this magnetism. Now few topics which we need to discuss. That is, I'll tell you.